So this is the second part of the first day of lecture, and we've got a lot to cover in the second part because you're going to be coming to class ready to do problems related to forces. So what we're going to do in this lecture is we're going to review forces and free body diagrams. Again, the assumption is that you've had this before in another class. So we're going to define those things again, and we're going to come up with a consistent way of drawing free body diagrams that I expect you to use in AP Physics. That's going to be a little bit different than what you might have learned unless you had me as a teacher. So be warned, this may be review, but we're going to add a couple of twists to it to make sure we're consistent in drawing things the same way. And we're going to use those free body diagrams to get into Newton's three laws. So we will do a review of the law of inertia and look at it in a little bit of a deeper way than you did in your last physics class. We're going to apply our method of drawing free body diagrams to solve problems using Newton's second law. And then finally, we're going to write down Newton's third law, which is the action-reaction law. And what's going to happen is by using the notation that I'm going to show you when I show you how to do free body diagrams my way, you're going to very easily be able to identify third law pairs in problems and solve problems algebraically. Then what we're going to do, and I don't know if we'll do this in this video lecture, but definitely in class, we're going to be doing problems with forces, and we're going to ultimately taking our knowledge of Newton's three laws and free body diagrams and forces and applying them to AP practice problems. So let's jump in and get started. All right, I want to spend this first little part talking about basically what forces are and kind of defining those properly. So to do that, let's get started with our definition of what a force is. So to define a force, I would say a force is nothing more than a push or a pull on an object. And that's as good a definition as we could hope for in AP Physics. So I just want to be clear. This definition is primitive, simple, and to the point. What I don't want to get into in AP Physics is a debate on, oh, well, what are forces really, and what does this mean, and all that kind of stuff. Let's talk about examples of forces. So examples of forces include things like gravity, tension, spring forces, electromagnetic forces, friction, contact forces. There's a whole host of other forces I haven't even bothered to name, nor am I going to. Just we know that there are these pushes and pulls that happen in nature, and we're going to call those things forces. Okay, and we know that they act because they make objects want to speed up or slow down or change direction. But there we're getting really into Newton's laws, which I don't want to spend time on yet, because what I want to get into now is how we represent forces in physics systems. So suppose, for example, I have a flat surface, which I'm drawing very badly, but oh well, it's the price we pay. And I've got a box on it, and this box is sitting on the ground. Now you remember from your last physics class, and this is kind of what we're going to be doing in AP Physics. So this is kind of like an intro, or rather a review of free body diagrams. Now here's the thing. What we're going to do first of all is suppose I have this mass M sitting on the floor. Now the first thing is we're going to represent this mass M as a point like this. And if you remember, this mass M wants to fall to the ground, so there should be an arrow pointed downwards that represents the weight of that mass. And remember, weight, okay, so we got a little definition here just to kind of review. Let's remember weight, okay, that's, if you remember, the effect Earth's gravity has on an object. Okay, it is not mass. Okay, and this is what I mean by AP Physics moves at a faster pace. We're not going to spend weeks explaining why and how in this. This is something you had in your previous physics class, so this should be a little bit of review. Now, if all we had acting on this mass was the Earth pulling it down, this mass would fall and fall and fall, but we actually have the floor pushing up on it. So we actually have what we call a normal force. And normal here, okay, normal force is a contact force perpendicular to the surface. And that's actually what the term normal means. We're using the term normal the way it's used in advanced calculus classes and geometry classes and analytic geometry. Normal doesn't mean like a normal person or, you know, a normal day. It means, you know, like regular or plain. Normal means perpendicular when we're talking about things like geometry. So normal actually means perpendicular. Now, here's the thing that we're going to be doing differently in AP Physics that I expect you to do in your free body diagrams. This normal force acts on the mass m because the surface is in contact with it. And this weight W acts on the mass because Earth pulls it. So when you label your free body diagrams, I expect you to write first subscript the object that feels the force, and then the object that causes it. And that's same with this normal force. It's the mass that feels the force, and it's the actual surface of the ground that causes this force. So that's something I want to be very clear on in the free body diagrams. So what we're going to do now is we're going to do a review of Newton's laws and hopefully have some time to draw some free body diagrams and practice this new notation. So if you have drawn free body diagrams any other way, you need to abandon that way. We're going to all get on this system of drawing free body diagrams this way now. So moving on to Newton's first law, which is the law of inertia. I actually had a version of it cut and paste here, so I actually want to read this carefully and talk a little bit about what it means, because there's a lot to this law and a lot that's implied. So it says, in the absence of a net external force, an object will, I should say, either, actually, you know what, let's leave either out of it, will remain at rest or in motion in a straight line at a constant speed. So let's be clear. There are three words here I want to be clear on. So force, once again from our last little part, is either a push or a pull. Now, external means outside the object. Now we're going to get a little bit deeper and talk about something called a system later on, but for now we're going to say outside an object. And what we mean by net is, another word that they use is unbalanced, or you'll see extra, or you'll see non-zero. All these different words. Let's be clear on what we mean. So there's this idea somehow that there's no force acting on an object. And when there's no force acting on an object, this first part makes sense. Well, if there's no force, there's no push or pull, well then the thing should sit still. And what this net external force says is, well, if I've got two forces acting, say one here and one here, and they balance, that's the case of no net external force. Well, I could see that an object would remain at rest. I'm fine with that. But then there's this second part which says, hey, if the thing was moving in a straight line at a constant speed, it's going to continue moving that way. So another way to say this is, an object that is moving at a straight line, at a constant speed will go on forever and ever and ever and ever and ever. In fact, that's so important that I actually want to restate the second law right now. So let me do that right down here. So another way of saying this is an object in motion will remain in motion in a straight line at a constant speed unless a net external force acts on it. Okay, so there are implications of this statement that I actually want to get clear on right now. So implications. Number one, if an object moves in a circle at a constant speed, there is a force acting on it. Okay, we're going to follow this definition literally. So it's not moving in a straight line. Whoops. Sorry about that. It's not moving in a straight line. That implies that there must be a force acting on it. Okay, so just to be clear. So another implication is that, let's see, so there's a little bit of weird typing here. Let me just get back in here. So there's a net force acting on it. Another one is if there can be forces acting on an object and it continue moving in a straight line and a constant speed. This means the forces are canceling. Okay, so that's one idea. Other implications. So this is a deep statement, so you may need to stop the video and read that over until you can make some sense of it. And if you don't, then this is something we need to discuss in class, and somebody needs to take the initiative to ask that question. So this means the forces are canceling each other. Canceling each other out. So lastly, if an object is sitting perfectly still, then there is no net force on it, i.e. the forces cancel out. So I want to actually kind of go into how this works with this object here. So I've got this mass m, and again, let's draw the forces on it like we did last time. So we have the normal force on the mass due to the surface, and we have the weight of the mass due to the earth. So there are two forces acting on this object, but the object doesn't move. What that implies is that the normal force has to exactly cancel the weight on the object by Newton's first law. So in other words, these two forces cancel each other out, so they must be equal in size, or the word we're going to use is these forces are equal in magnitude. I will use that word a lot. In fact, that word is so important, I'm going to write it in red. So magnitude is another way of saying size. You might want to review that because that's going to be one of the questions in the Google Docs. So they are equal in magnitude. So that really kind of sums up what we know about Newton's first law. And once again, just want to say it one more time. If I've got an object in outer space moving with a speed v0, it will continue that way forever and ever and ever and ever and ever and ever and ever till the end of time or the end of days or whatever. Should it not do that? Should it change direction? Should it stop? That can only happen because a force acts on it.